Thank you so much for the introduction. Today I'll be presenting our work, Venice, Improving Solid-State Drive Parallelism at Low Cost via Conflict-Free Access. Now let's look at the outline of the talk. And here I'd start by providing a brief motivation for this work. Here we look at a very high-level overview of the modern solid-state drive. An SSD has a solid-state SSD controller, which has several components in it, such as the host interface layer to communicate with the host, the flash translation layer, which performs many functionalities such as garbage collection, word leveling, and address translation. There's also a DRAM component to cache frequently accessed data in the SSD. And there are several flash controllers which manage flash chips using shared channels. Now let's look at the problem that we address in this work. In commodity SSDs, multiple flash memory chips are connected to the SSD controller using a shared channel. I/O requests in data-intensive workloads attempt to simultaneously access the flash chips using a single path, which cause path conflicts in SSDs. And path conflicts cause I/O requests to be transferred serially on the shared channel, which limits SSD parallelism and reduces the overall system performance. Now let's look at the delay caused by path conflicts. Here we show two cases. In the first case, we show two read requests which simultaneously arrive targeting flash chips connected to the same channel. And here, these requests experience path conflict. And if we see the timeline of how these requests are served, we show three steps of the read request: command transfer over the channel, the read operation within the flash chips, and the data transfer over the channel. And in this case, the command transfer and the data transfer steps are served serially because of the single shared channel. Now, if we look at another case where two read requests target flash chips connected to different channels, they are served in parallel. And if you look at the timeline, the three steps are completely served in parallel, which saves a lot of cycles. Now, if you look at the performance impact of path conflicts increase the average I/O latency by 57% in our experiments on a performance-optimized SSD, and this is considering only two requests. The performance overhead of path conflicts increases by 1.6 times for high-intensity workloads. Now, we look at some prior approaches. We have the baseline SSD, which uses a multi-channel shared bus architecture, and packetized SSD, which increases the channel bandwidth by 2 times to reduce the transfer latency. These approaches do not provide path diversity to flash chips, which means that each flash chip can be accessed using a single path. Now we look at another work, which is packetized network SSD, which introduces vertical channels to increase the path diversity. And here we can see that each flash chip can be accessed by 2 paths. And we also have network on SSD, a prior work which introduces an interconnection network of flash chips. These approaches do not effectively utilize the path diversity and incur large area and cost overhead. So our goal in this work is to fundamentally address the path conflict problem in SSDs by increasing the number of paths to each flash chip at low cost, and effectively utilizing the increased path diversity for communication between the SSD controller and the flash chips. To this end, we propose Venice. Venice has 3 key components: a low-cost interconnection network of flash chips in the SSD, conflict-free path reservation for each I/O request, and a non-minimal fully adaptive routing algorithm for path identification. Now let's start by looking at the architecture of Venice. Venice has an interconnection network of flash nodes, which are connected using bidirectional links. Here we show a 2D mesh topology, but Venice in principle can work with any network topology. And if we see the structure of a flash node, we have a commodity flash chip and a router chip placed next to the flash chip. The bidirectional links are directly connected to the router chip, and the flash chip and the router chip communicate with each other using the typical I/O data pins. Now, Venice provides increased path diversity at low cost, and existing flash chips do not require any modifications in Venice. Now we look at the conflict-free path reservation for each I/O request, and Venice uses a small scout packet to reserve a conflict-free path for each I/O request. And this path reservation process happens before the I/O request transfer is done. Here we see a configuration where we have 4 flash controllers and 20 flash nodes. And an I/O request whose target flash node is F8. Venice sends a scout packet using the flash controller FC1 through the network to reserve a path before the I/O request is actually transferred. So the scout packet traverses the network, and whenever it reaches an intermediate flash node, the router inside the flash node actually adds an entry into its router reservation table to reserve the links used by the scout packet. And this process happens for every flash node that the scout packet traverses through. And the scout packet continues and reaches the destination node. And when it reaches the destination node, the scout packet returns to the flash controller to confirm the path reservation process. And this reserved path can now be utilized by the IO request for conflict-free data transfer or command transfer. Now, if we look at another example where an IO request, the target flash node for an IO request is F9, and this IO request would typically face path conflict in a commodity SSD because the channel is already occupied by another request. So, but in Venice, we can use any flash controller to send the request to the target flash node F9. And here we show the path reservation process through FC2. So this is the reserve path for F9. So path reservation process eliminates path conflicts by enabling conflict-free IO transfer, and the overhead of path reservation is negligible due to the small size of the scout packet. Next, we look at the routing algorithm for path identification used in Venice. And Venice uses a non-minimal fully adaptive routing algorithm to route scout packets when a minimal path is unavailable. And this routing algorithm effectively utilizes the idle links in the interconnection network to find a conflict-free path. We show this using a network here, and we will show three IO requests for which the path reservation is done. And we see that for a request F to F8, the path reservation is done using FC1. For F6, it goes through FC0. And for F7, the path reservation is done using FC2. And these three IO requests, the path reservation is done using minimal paths. Now we look at another request for which the target flash node is F2, and we cannot serve or do path reservation using minimal path for this because the links leading to this target flash node are occupied by other IO requests. So Venice uses the idle links in the network to reserve a conflict-free path, conflict-free non-minimal path for this IO request, as we can see here. We have a lot more design aspects of Venice in the paper, such as handling deadlock and live lock scenarios, overhead of exercising a non-minimal path, and I would encourage everyone to take a look at the paper. Next, we look at the evaluation of Venice. Venice and prior approaches are evaluated using MQSim, a state-of-the-art SSD simulator, and we use two SSD configurations to evaluate Venice and prior approaches. We have a performance-optimized configuration based on Samsung Z-NAND SSD and cost-optimized configuration based on a Samsung TLC NAND SSD. We choose 19 data-intensive storage workloads from a variety of sources, and we implement several prior approaches that we have discussed earlier, along with a path conflict-free SSD, which is an ideal SSD where IO requests do not experience any path conflicts. Now let's look at some results. We show the performance for Venice and prior approaches on a performance-optimized SSD, and here we show the speed up over baseline SSD for Venice and prior approaches. Venice is shown in green here, and we see that Venice improves SSD performance by 1.9 times on average over the best performing prior approach. And Venice's performance is within 45% of the performance of a path conflict-free SSD. Now, we also look at the results for a cost-optimized SSD, and we see a similar trend here as well. And we show the speed up again, and Venice improves SSD performance by 1.5 times on average over the best performing prior approach. And Venice's performance is within 25% of the performance of the path conflict-free SSD. Next, so overall, Venice provides significant performance improvement over all prior approaches on a wide variety of workloads. Next, we look at the reduction in path conflicts. Here we show the percentage of IO requests for each workload which experiences path conflict, and we show the prior approaches and Venice here. And with Venice, 99.98% of the IO requests do not experience any path conflicts. And this is because of the path reservation process and effective utilization of path diversity. We finally look at the SSD energy consumption, and here we show the energy consumption normalized to a baseline multi-channel shared bus architecture SSD, and we show that we see that Venice reduces the energy consumption by 61% over a baseline SSD and by 46% on average over the most efficient prior work. We have a lot more results and analysis in the paper. We show the power and area overhead analysis, tail latency analysis, and sensitivity to different interconnection network configurations. And I would encourage everyone to take a look at that. This is the link to the archive version of the paper. So in summary, Venice mitigates path conflicts by efficiently utilizing the path diversity of the SSD interconnection network. Compared to the best performing prior approach, Venice improves performance by 1.9 times on a performance optimized configuration and 1.5 times on a cost optimized SSD configuration. Compared to the most efficient prior approach, Venice reduces energy consumption by 46% on average. And the benefits of Venice come at a very low cost and requires no changes to commodity flash chips. I'll conclude my talk here. Thank you for your patience, and I'll be happy to take questions.
Okay, time for questions.
Andreas Koch, Darmstadt. Can you give a rough impression of the relative times required for the path reservation step and serving the actual request?
So from our experiments, the path reservation step takes around 40 cycles at max, so around 40 nanoseconds, compared to the actual IO transfer, which is for a 16 KB page. It takes around around 16 microseconds. So it's an order of magnitude less than the actual page transfer.
Thank you.
Thank you for the talk. I'm Hans from KAIS. Can you provide comments on the overhead of adding router in terms of the flash chip area? And then can you also give comment on how you can get such big improvement in terms of energy consumption with the additional router for the flash chips?
Yeah, that's a great question. Thank you. So in terms of the area overhead, the router that we add it takes around 8% of the flash chip area. And the reason why we get a good energy consumption results is because the overall execution time is reduced because of Venice, and also the components used by Venice, such as the router and the network links, consume less power than a typical shared bus architecture. So that's the reason why we get better efficiency.
Okay. Any other question? Actually, I have one question myself. So in your path reservation, you need to reserve the path for every single record request per record request basis. So it automatically, once you actually go through the real a payload is read out, then you basically automatically tear down all these paths. You don't need a separate tear down process for this reserved path. Is it my understanding correct?
The question, please.
Because you actually send a scout packet to actually reserve all these paths, right?
Yes.
And then you actually read out, access this chip to actually read the payload, and then at that point automatically this reservation is basically tear down. Is it
exactly
correct?
So the router takes care of the path reservation process. We do not interact with the flash chip at that point, and when the IO request has to be transferred, the flash chip will be activated.
Yep. Okay. All right. Yeah. Thank you very much, Rakesh.
Thank you.
Very nice talk.